Hello everyone, and welcome back again to the second part of Introduction to Computer Graphics. Now in this, let me just close this tab. I don't know, I had it opened from a previous session. Okay, in this session we're going to be continuing building upon the previous concepts which I was talking about. And in the last part I was talking about how we could actually transform points. So we had the very simple coordinate system here, and again, let me try to Control Z that, try to get a little bit straighter line like this. Okay, it's a little bit, you know, my recording software is grabbing in a weird way. Tablet. Okay, so there you go. So we have a triangle, or at least I had a triangle. Let me grab the red color from the last part so we can be consistent. So we had a simple triangle that that we started to transform, translate, and rotate. Okay. This is really weird, but anyway. It actually as well started to glitch at the first lesson like that, but anyway. And here we had the coordinates 1 and 0. Apparently today the tablet won't comply somehow. Alright, so we see here. Okay, it can work. Sorry about that, guys. Just be patient with me here. Somehow I'm having a little bit of technical difficulties here. So this is 1 0 0 1 and -1 and 0. So we had these three coordinates, this triangle, and we were trying to transform it by rotating it, scaling it, and translating it. And there was a z-axis, but basically we weren't using it. We were just transforming according to 2D, because this is mathematically, I mean, we don't need to spend a lot of time of writing extra or calculating extra numbers, since anyway we are plotting on 2D board here. And yes, Armin Z is the depth. Now here we are looking at let me just get my white here. So we're looking at, this is the positive y, this is the positive x. Now the last time we stopped at the part when we were talking about transformation matrices, and I said back then that if you would like to transform a 3D object, what we could do is merge two vertices into one by multiplying them. So if I would like to rotate this triangle and scale it at the same time, we need to you know, and do all this in one step, because if you, for example, if I say matrix A is my rotation, for example, and multiplied by matrix B, which is my scale, we're gonna get a matrix M, which combines the rotation and scaling. Okay, so this is what we get when we multiply two matrices together. You get these two operations are actually being merged into one. And what I could do here is grab this matrix M, multiply it by this point, and it will immediately scale that point. Scale it by mean moving it somewhere, actually, like scale that point, it means like it really shifts it somewhere according to this coordinates which already mentioned here, and rotates it somewhere else. Now the last lesson we were trying to scale this triangle twice actually its size, so we are actually multiplying its size by 2, and we were trying to rotating it 90 degrees, and when we multiplied, for example, one vector, which was this one, after scaling it and rotating it 90 degrees that way, okay, now we ended up with a triangle that looks like this. After scaling and rotating at the same time, we ended up with something that looks like this. So we have 0, 2, and we have here -1 and 0, and we have one more, sorry, just accept, and we have one more here, and actually it should be somewhere right there, I think, yeah, somewhere here. And then we had, you know, a scaled version of the triangle after rotating it and translating it, after rotating it and scaling it. All right. So this is actually what happened when I multiplied every single vector or every single point by that matrix M. So I multiplied it by my V. Now here is the problem. I could actually rotate and scale, and I could do that in one operation. However, because they are multiplicative operation by nature, they actually could be merged easily, because the only way to keep two matrices, to merge them into one, you have to multiply them together. However, if I would like to do one more operation, which is translating or moving the triangle, so I would like to rotate, scale, translate the triangle, you end up with a problem here, because translation is an additive operation by its nature. You need to add to these vertices. You need to add to those guys in order for you to move them along. So if I would like to move this triangle, add to each vertex, or add to each vertex a vector, and then you end up with the new position. Now, hi man. Now, hi Imad. Now we have the new matrix. We need to define a matrix for translation. Okay. Now that matrix of translation, we have to find a way to integrate it, or I mean to have this. Hang on a sec. Actually, you know what? Before I go into the matrix form, our formula would look like this up until now without matrices. So without the translation matrix. So we end up with something like this. So the rotation A, so matrix of rotation A, times the matrix rotation B, then plus your translation operation, which is adding a vector, you know, to every of those, to adding a vector to these guys, you know. And the problem is we would like to push this guy here. However, it cannot be happening because of addition, and we cannot end up with another matrix, let's say another big M, you know, that encompasses or it contains as well translation. So what we could do here, now people were actually like trying to resolve this problem, and the suggestion was, all right, then what we would do is add one more dimension, and this is what the homogeneous coordinate systems is about. So our vector will exist, will have the following coordinates: x, you just put x normally here, x, y, and we add here 1. Okay, and then we multiply it by the following matrix. Now again, the proof of that matrix you can follow along with Professor Zain in his materials, so that's why I will not actually go in details how this translation matrix was formed, but anyway, I will keep it simple here. So I will go say 1 0 0 1 0 0. Then we have translation in X, translation in Y, translation, actually not translation anymore, right here it has to be 1, like that. Now the question is, what is that thing, right? According to the homogeneous coordinate system, yes, it's diagonal. According to the homogeneous coordinate system, this is W. So this is your X, this is your Y, and this is called W. In fact, he called the guy who invented it, he called it W. However, if you think about it, our triangle is being pushed in another dimension, in one more dimension higher, sheared, and then it will be pushed back again to its original dimension. No, it is not an identity matrix because of this. You see? This, because of this, it cannot be an identity matrix. It would be an identity matrix if it's going to be 0 0 here, but it's not. Let me do this so not to make it a little bit crowdy. So if we multiply with this mathematical trick, if we multiply this vector by this weird matrix, we will end up with something. We will end up with the additive operation here. So you see, X multiplied by 1 plus Y multiplied by 0 plus 1 times whatever number you're going to translate. Then again, X times 0 plus Y times 1 plus one times ty, okay, and then we have X times 0 plus Y times 0 plus 1 times 1. You see what we have got here? We have got a new vector with this additive operation. This is 0, this is 0, 0, 0. So you end up with X plus Tx, and Tx is the number to add, to move the object alright, and Y plus hang on a sec, plus Ty and 1. You see? So right now the matrix became, we added one more dimension, and right now we can actually multiply and we get translation instead of just adding, right? And with the multiplication, by adding this new dimension, we get this additive part with us. So we successfully actually could move at a certain point from one position to another, and this is why we have this coordinate system, this homogeneous coordinate system. And by the way, it's not only used in computer graphics; it's used in any. I think you can find it even in the fields of robotics. If you would like to move a robotic arm, rotate a robotic arm, you're gonna have to utilize almost exactly the same matrices, which I'm utilizing here. Now, of course, when they have discovered this, they said, okay, for every matrix, we're gonna add one more dimension, which is gonna be the W dimension, where we're gonna actually we're gonna have this, scaling and for rotation and for translation. And then when you would like to move, translate, and rotate a certain object all at once, you just simply multiply those three matrices, major matrices operations together. You end up with a matrix M that if you multiply it by the V vertex or vector, you end up with the 3D object being transformed in rotation, scaling, and translation all at once in one shot. And if we work with matrices, like for example for scaling, you will end up with a scaling that's not 2 by 2 anymore. So for example, if I'd like to scale a 2D object, somehow erase, I cannot erase anymore probably. Well, let me see here, 2 0 0 1 0 0. This is how your scaling matrix in 2-dimension looks like. The rotation as well looks pretty much the same. You have your cosine and sines. However, the last row here is your double dimension, which you shouldn't touch. And here, of course, you get this cosine theta minus sine theta, and then sine theta and cosine. Oh, I think it's cosine. I hope that I didn't forget the exact numbers here. I hope that I didn't mix them up. But anyway, this is basically the how it looks like after adding this single dimension. Now the most interesting part here is you are pushing objects out of their dimensions. If we are rotating, if you are, for example, let's say not rotating, let's say if you are trying to translate a certain object in 3 dimensions, you know, its translation matrix will have 4 dimensions. So we're gonna have 1 1 1. Opa, I think I'm losing the thing here. So 1 1 1 0 0 0 0 0 0 and 0 0 0 0. Actually, it shouldn't be 0 here. It should be for some crazy reason. Let me try to erase this with a color like that. X. Now you're gonna get here tx, ty, tz. You see, your object is moved into the 4th dimension. Okay, now of course you cannot imagine the 4th dimension at all. You won't see it, you cannot picture it, but what's happening here is your object is being moved to a single plane on the 4th dimension, sheared in the 4th dimension. Then we cast its shadow back to the 3rd dimension, and then you get the 3D object displayed in front of you. And when we were translating the 2D object, we took this 2D object, we put it on a single plane in 3D. All right, we sheared it, and then we casted its shadow back to the 2nd dimension again, to the 2 dimensions again, and then we saw our object. If you cannot picture this, a point is 1 dimension, right? A line is composed of infinite number of points, right? So a line is composed of infinite number of points. Now that means that a single line, which is a 2D, okay, so a dot is 1D, a line is 2D, and a line is composed of, or 2D is composed of infinite number of single dimensional planes. All right, because a point is a single dimension, so, and the point is you have an infinite number of points on a single line, so the line, which is a 2D thing, actually composed of infinite numbers of of dots or infinite numbers of one-dimensional plane. 3D, all right, now we're talking like moving one higher dimension. 3D, a 3D is composed of infinite number of 2D planes. 4D is composed of infinite numbers of 3D planes. Now this could be actually kind of weird for you to picture, so that's why you cannot actually imagine how the 4-dimensional looks like. By the way, some people take the 4th dimension as the temporal dimension, which they say the time, and when we are talking here about the 4th dimension, we are talking about the fourth dimension as a coordinate rather than temporal, which is very, very, very important. Okay, now for those who are interested, you can actually look at the tesseract or a hypercube, for example, to see how a cube, for example, may look like in the 4th dimension. However, whatever kind of representation of a cube, which looks like of a cube that exists in the 4th dimension, or any cube, any hypercube, representing it in 3D world, in the world which we live in, it won't be accurate at all. It will be impossible to represent, because whatever you see a 4D object in the 3D world, you just see the shadow of it. You see just only part of it, one plane of it. You don't see several planes. You just see only one plane of it. Anyway, so this is actually what's happening. And I think when you are working with Unity, you will see only those three, I think. And if you are using OpenGL or DirectX or whatever, you will not be seeing those. Maybe you will be, when we are starting working with shaders and multiplying vectors and matrices together. Right now, you're gonna have to really utilize all the 4 dimensions and then do all these transformations. However, in Unity, I think they are really hidden from you, or most game engines are really hiding this from you. Now, here's one more question: how we return back? I mean, I was talking all the fun stuff about the multi-dimensional thingies, all right, and we moving the 2D object into a 3rd dimensional plane, and then we cast its shadow back to the 2 dimensions. Now, how we are actually moving this guy back? And we are moving it back by dividing this number, by dividing these guys by this number. Okay, now here's the interesting part. If this is 1, if this becomes 1 and always 1, that means you're gonna flat whatever exists in that dimension and reduce it to 1. Okay, so for example, you had a triangle that exists on a plane on a 3rd dimension, and then you would like to return it back to its original dimension. You have to divide it by that number. Now, if you divide it by that number, when it comes to 1, it will actually, whatever it was, it will actually just return back to to that plane. If in homogeneous coordinate system, if this number becomes a 0, if this becomes 0, now you run into a very interesting problem, and a feature, in fact. If you divide this number by a 0 in homogeneous coordinate system, you get something which is called a direction. Okay, and this is how you get the parallax effect, or you get, for example, the effect of when you are standing on on a train track, and you see the 2 tracks are meeting at a certain point at infinity. You know when you are standing on a train track, just please do not stand on a train track. Don't say that Muhammad told you stand on a train track. It's a bad idea. But if you happen to be standing on one, and you shouldn't wait for the train, please, so don't do that as well. It's a bad idea, not recommended at all. And if you see a train coming at you and it horns at you, get out of the way. So right now nobody can sue me and say Muhammad is telling students to stand on train tracks and all these stuff. Okay, so this is a train track, and whenever you're standing on a train track, these are 2 parallel lines. However, they meet at a certain point, and this point is called the mathematicians actually have concluded that this is the point of infinity. Okay, because parallel lines, according to Euclidean math, parallel lines, they never meet. However, they meet at a certain point. When you stand and look, they are meeting at a certain point. So this is called the point of infinity. Now, if you divide that number, these guys, by 0, you get a certain direction, which with it, you could start simulating these kind of effects. Okay, this is the point about why we need the fourth dimension and what kind of benefits we get. So we get, or the third dimension, or adding a dimension to our matrices. We solve the problem of taking our translation matrix, we can actually multiply it by rotation and scaling, and then we could end up with a huge, nice final matrix M that it could encompass or hold all these transformations all at the same time. So yeah, this is the part about why we have one more dimension added to our matrices. Do you guys have any questions regarding that part before I move along to other points? Good. Good. Okay. Now I will erase this all beautiful and gone. I know what you can do. Now let's move to the next point. And the point here is we haven't done yet. We don't have any glowing pixels on our screens yet. And this is kind of frustrating, of course. I mean, after all the video cards job and processing job of how to do transformations, translate that object, put it there, you know, position it everywhere, and then you would like to convert it into a glowing pixels. It's still, you still have not finished all the transformations yet, just to make it a glowing pixel on your screen. Okay, and this is the part when it comes to completing the transformations. So you, as a programmer, you have done moving a 3D object in 3D space or in 2D space. Now what you need to do is represent it as glowing pixels on the screen. In order to achieve that, you need to go through another series of transformations. Because transformations are not only scaling, rotating, and translating, you have more of them in computer graphics. Now, if you remember from yesterday's lesson, or not yesterday, actually the last time's lesson, I was talking about describing a 2D object and describing its local coordinates and global coordinates versus the global coordinates. Yes. So this is y, this is x, right? And if this is my global one, which is, this is x, and this is y, or the world one. Now I need, if I take this guy and if I rotate him like this, right? And enter. So right now this object locally is described by having the y is pointing right there and the x is pointing right there, completely the opposite to the world. Okay. Zašto je centar koordinatnog sistema kod PC u lijevom uglu? Do you mean the top left? Why the 0, 0 at the top left? I really don't know. Cool question. I really don't know. I never thought about it. But anyway, maybe probably it's gonna be tied to some sort of I think most of the I mean, if you trace the PC history, most of the standards have been happening because of some technical limitations, right? and then after the technology has evolved, everybody was using the standard somehow, so you never know why it was there, but I will actually research it. It's very interesting. Inače, može biti 8 načina crtanja koordinatnog sistema. What do you mean by 8 ways of drawing coordinate systems? Aha, 8 ways, like every corner, your coordinate system could start from every corner, from any corner, right? So this is 4. Where else would you like to have it? You have only 5, I think. So your 0, 0 could be here, or there, or here, or there, or at the center, is it? In fact, in 3D graphics, you can define your coordinate system anywhere you like on the screen. You know, why the operating system chosen this part? I would like actually to search about this part. Maybe if I find the answer, I will actually tell you about it in the next lesson. But yeah, it's a very interesting question indeed. All right. Now, okay, I would like to move along. So regarding this, so we describe the object. When we describe it according to its local coordinates, as I already said. Now we need to put this object somewhere in the world. All right. So we immediately transform it, right, to its world coordinates. So we have from the object space, going from the object space, we are pushing it into the world space, and this is another matrix, by the way. Okay, and after doing that, we need to put this object in front of our eyes so we could see it, right? Because I mean, imagine yourself, you are standing here, right, and then somebody else you have a ball behind you. You are sitting on your chair in your room, and there's a ball behind you. I can put anything in your room, which is, let's say, your world coordinates, and you will never know about it unless that object which I'm putting in your room will start appearing in your eye range, right, into your eyes range. So right there, this is where you need to transform all your objects to the eye space or camera space. Okay, the transformation from the object space to the world space and to the camera space. So if you would like to go from, so this is the OBJ object space to the world space to the camera space. Oh man, why my handwriting is really cool with this tablet, I have to admit. Okay. Camera space, or your eye space. Okay, you have from here to here. This is called the model view transformation. In the old standards of OpenGL, you have a model view matrix. Okay, it's called model view. By the way, I'm writing in that direction because this is how my tablet is oriented. I really cannot orient it other ways, so please bear with me here. Anyway, this model view transformation, it's called like that, and in the old OpenGL standard, you have the model view matrix already existing for you, which you can actually use, by the way. And if you are programming using the OpenGL's new standards, where you have this programmable pipeline, you have the model matrix separate, your view matrix is separate, and of course your projection matrix is separate, and you have to multiply them together to to have to multiply the model view and the projection, guys. So in order for you to get the final matrix, which through which if you multiply every vertex by if you multiply every vertex of your object, your 3D object, by this model view projection matrix, you get the 3D object rendered right away in front of your screen. Okay. Now, however, this is not all. Okay. Now the problem is, if you have two-dimensional thing or a three-dimensional thing, they still exist in the other dimension, which is either the third or the fourth dimension. I need to reduce them to two dimensions. All right. So what you need to do is flatten everything out. Just squash everything out towards your screen, and this is flatten everything out and clipping everything out of the site, out of the edges of your screen. For example, if a 3D object is outside of your range of your screen, right now this is the part where it goes your homogeneous clip space, where everything starts squashing to your screen and clipped out if some part of the object doesn't exist. For example, if you look, if I say this is your monitor, and you have, for example, a triangle which is yay big, the computer needs to only worry about this part, okay, and discard these guys. These guys has to be clipped out. So these guys has to be clipped. Okay? So this is what clipping is about. Let me show you a summary of the transformation which I was talking about. Here is your objects coming from the object space being transformed to the world space, and from the world space coming back to the camera space. So we are moving everything towards the camera. You know, this is actually the funny part. In computer graphics, of course, I mean, at least, okay, in the real world, we have to move our cameras. You are holding your phone camera, and you are moving, for example, your phone towards, for example, the pyramids. If you are a tourist in Egypt and you are trying to see the pyramids, you move your camera, your cell phone or whatever, your digital camera, towards the pyramid, and then you take a snapshot. In computer graphics, we are a bunch of hulks. We actually move the whole pyramids in front of our cameras. And if you think about it, in both ways, it is actually pretty much the same. Whether the pyramid actually has moved or the camera has moved, you get this pretty much the same effect. So that's why what we do here, especially in this part, at least in this transformation, we are really removing everything, the whole world. If you have modeled a whole city, the whole city just moves toward the camera, which is this is the coolest part about the story of transformations. And yeah, and then you go ahead to and then you move on to projection. Then you go back to viewport transformation, where everything will be clipped nice and neat and then shown on your window. Okay, on your window, for example, like in this area, for example, this is what I'm talking about, the window space. Okay, so this is what's happening when you are transforming a 3D object or a 2D object from being just created until it gets you know, rendered on the screen, like until it gets squashed and shown on your 2D screen. Now the interesting part here is we are not done yet, and we still don't have pixels yet. Now in order to have pixels on our screen, we are passing through something which is called the rasterization process. Now what the rasterization process is about is, let me grab very simple form here. I'll try to create a row of pixels, and it's actually extremely huge. Extremely huge pixels. but hey, I think it will serve the purpose, which actually introduces a lot of interesting algorithms and problems of how to represent straight lines on such a grid. One of the most famous ones is, I think, Brisenham's algorithm for drawing, for example, a line. How to draw a line on a grid, you know what I mean? It's like, for example, if you are drawing a diagonal line, I cannot draw this like that, because when you zoom out, you will end up with a line that looks like this, somewhat like that. So at the end, you end up with something like that, right? And then it depends, I mean, how you are actually reaching this. And you could see it a lot in I mean, you can see it a lot here. For example, like if I draw this is a straight line, by the way. And let me zoom in even more. You see, a straight line is in fact not very straight anyway. It's a bunch of pixels. Now, of course, since I have shades, actually some sort of a smoothness to the edges of this line, it appears to be so, but in fact it's jagged, you see. And you have a lot of algorithms of how to smooth these lines. Anyway, let's move on to our triangle problem here. So if I get our triangle right there, and I will try to draw it. Yes, Armin, actually anti-aliasing is also about how to remove this not real-time, this jaggedness out of these lines. But it's actually another story. Now, what happens here is you are giving the computer the triangle, and you are telling the computer, okay, please convert this for me into pixels. And what it does is it takes the triangle like this, and it says, okay, is this triangle, is this pixel is inside this triangle? And if it is yes, then we're gonna actually make it glow. So we make it glow, right? Is this pixel is inside this triangle? And it says yes, so I'm gonna make this thing glows. Is this guy is inside? Well, it's not, let's say, so it will ignore that part. Is this pixel is inside this triangle? It will say yes. It's inside here, inside there. For the sake of the argument, it's here. For the sake of the argument, it's inside. Okay, we will ignore this one, and we're gonna grab that one, for example. And okay, we'll grab this one, for example, and this is it. And this is your very ultimate low-res triangle of all time. And this is because I have pixels of a size of, it's like 2 centimeters by 1 centimeter or something like that. So you can get a glowing triangle for you. Okay, and this is how the computer actually rasterizes it. Now here comes the problem. What happens if I have 2 triangles? Right? You have a triangle A and you have a triangle B. And what happens if triangle A suddenly comes above, in front of triangle B? And this is where it happens. This is where you start getting certain glitches, like certain weird problems. For example, let's say, let me just erase this, and for the sake of the argument, I'll make these 2 triangles like this, or in fact even I'll make it even more closer like this. So this triangle B, and I will in fact, just to make it different, right? And I will grab the red color here, and I will make this triangle B. okay? And this is triangle A. This poor little guy who's eclipsed by the large, big, bully triangle B, okay? And now you are actually drawing, you know, and you say, okay, triangle A, I would like to position it at, let's say, 0 in X, 0 in Y, and I will position it 4 in Z. And I will say, okay, for the, yeah, again, apparently I cannot draw here. Hang on a sec. I'll try to erase this guy. So I'll put a point here, one there. Okay, and I will have triangle B at, let's say I shifted here 1, 0, and I'll put it, let's say, I'll put it 6. And I say, please draw triangle A and triangle B. Now the order is going to start to matter, because if I said B, actually if I pass to the computer, draw B, then draw A, what's going to happen here is you draw B first, and then you draw A, and this is where it comes to, you know, you're gonna end up with reversed order. You're gonna get A is in front of B, while B is in fact in front of A. You see, because the last guy who was drawn, you will actually get the, how can I say, the priority. You see, I will draw B first. So this is B, and then I will just simply draw A above it right away. Now A gets overridden. Now I mean A overrides B right now, just because of the order of the drawing, and this is actually wasting even more performance, because right now I am actually drawing 2 triangles instead of drawing 1 1/4 of a triangle. You see, the pixels behind the B, the pixels of the A triangle, which is for the B triangle, which is standing right here, is not visible anyway. You don't need to draw them. Now in this case we are drawing them anyway, because I said draw B, then draw A. And this is where it comes the depth buffering. What the depth buffer does is trying to save the information, the depth information of a pixel. So it says, okay, is this pixel is behind of any other pixels? And it says, if the computer says no, then just make this pixel glow. Now it comes over here at this point for the A triangle, and it says, is this pixel is behind another pixel, or behind, if this point in the triangle is behind another triangle, or this point of pixel is behind other pixel. And if it says yes, this pixel is behind another pixel, it will actually discard it and it will not draw it. Okay, now drawing this way using the depth buffer is much faster and much easier to resolve these kind of problems. And in fact, you can resolve along with it problems about lighting, about shading, and other and shadows actually with the depth buffers as well. This way of drawing without depth buffering, drawing the first triangle completely, then drawing the next triangle completely, is called the painter's algorithm. If you go and ask any artist, painter, they actually draw the background first. Then they draw above the background the characters or the scene, and they overlay and overlay a lot of objects until they get the final scene. You see, so that's why it's called the painter's algorithm. Okay, now the painter's algorithm, for example, could be utilized to resolve the issues of transparency. If I have a window, if I have a window like this in my scene, I'm inside a house in a scene, right? This is my window, and here is a tree somewhere outside in this world, you know, and mountains and clouds and sunny day and all these stuff, and you are looking through. If we are utilizing the depth buffer, if the window is, even if it is transparent, you will not see anything behind that window, and this is because your window is actually is standing in front of other objects. So it will ask, is this tree is behind that window? If it is yes, do not render it. And this is the problem could be resolved, for example, using this painter's algorithm. So you could, for example, disable the depth buffer, draw according to everything according to order. So you draw, I think you draw the world, outside world first, and then you draw your window, and then you enable the depth buffering afterwards, and everything will go just fine. So you have to do this trick: disable the depth testing for a while, do everything which you want according to the painter's algorithm, and then turn on the depth testing again, so you can get so you will not get any weird kind of effects. Armin, I don't understand. You've written weird characters actually, and then I get Razika at the end. I don't know what was AX go not well, okay, yeah, okay, now I see, but this is actually not about how it was Scoopery. I think it was not collections, it was ranges, or I cannot really remember, but right, I cannot remember exactly the translation in English, but no, it is not about that at all. Actually, these are the game with these stuff are about the union Boolean. Like, you can actually use the idea of Scooper, you can utilize it in cryptographics combined with Boolean operations like union, subtracting, intersecting, and all these stuff. It's a completely different thing. Actually, it's not a collection. It has actually a different name, a term, actually, a mathematical term. I cannot remember it right now, honestly. No, I mean, not the logic at all. The logic is completely different. It's a completely different story. You see, one happens to be in front of the other. Nothing about this part of the world, you know. Well, yeah. You could think of it that way. You could think of it that way, but it's a little bit different. I think it's a little bit different than. But yeah, you can think of it that way. Regarding the rasterization process. So yeah, you could for example say, if the pixel if this pixel is actually happening to belong to triangle A or not. But here is the interesting part. When you are actually squashing everything and you are transforming everything to pixels, the only information which you can hold about all the information about the 3D objects actually is gone. You lost all the information. So you have more like, it's not about without the depth buffering. Right now, without the depth buffering, it's right now not about which triangle anymore. Computer doesn't see any doesn't see triangle A, triangle B anymore. It sees something. I mean, if we look at this, it sees something just like this, and it just has to draw it. It just has to convert it to a bunch of pixels. It doesn't care, or it doesn't know even who is A and who is B anymore. When we introduce depth buffering, right now we are starting to keep track of things. Like this pixel is behind a certain pixel, and this pixel is in front of another pixel. You see, you got that information added. You know, this is how the process is going. You know. It's somehow close when it comes to Scoopery, but not that close. I think. All right. Okay. So just to summarize everything here, from the last session, we were talking about how a 3D object or how a 2D object is represented in computer graphics, and then moving from 2D to 3D. And doing 3D, moving 3D objects in 3D space, and then using transformation matrices, we transform them, scale them, rotate them, translate them, and then we do a series of other transformations in order to push them back again into in front of our camera, in front of our world, and squash them against our screen, and then start rasterizing them, okay? Until they become glowing pixels on our screen. So this was actually the journey. You can call it like a journey of a pixel, from being just an obscure, like kind of mathematical point, or representing the memory using 2 numbers or 3 or 4 numbers, and then it becomes just a glowing dot on your screen. This is how the journey comes from the code till glowing pixels. All right. Are there any questions regarding the process which we were talking about today? No, I'm actually done. So this is actually the this is the end of this session. In fact, this is the end of 2 parts, the introductory parts. You will get more when we get there, actually. When we start working with OpenGL a little bit, when we start working with Unity and all, this is the fun part starts. You know, when we start creating things, moving things around. Yeah. All right. Since there are no questions regarding the session, I will end this recording, and thanks all for your attention, and see you next time.